Hi everyone, thanks for coming. My name's Pollack. I'm an engineer at NAPSTER, and today we're going to talk about the failover mechanism in Redis. So the title is Too Big to Fail Over, a cautionary tale of scaling Redis. So problems my team experienced scaling Redis and sort of how we're going to approach them. So what are we going to talk about today? So first, how we use Redis at NAPSTER, the problems with the failover at scale. So as data grows in memory, how the failover mechanism takes longer to recover the slave and then read from the slave. And then finally, the solution that we came up with for constant time failovers. So first, I got to address the elephant in the room. I've been asked a couple times, but yes, Napster's still around. Rhapsody International, the streaming service that spun out of Real Network, rebranded as Napster last spring, so about a year ago. We provide an on-demand streaming app for our own users. That's with a mobile app and desktop. And then we also offer streaming as a service. So the iHeartRadio app uses us to stream our 40 million track catalog to their users as well. All right, so about what my team does. So we are the API gateway layer, or the basically the entry point into our system that all of our third-party developers and our internal apps use. And the way Redis is used for us is we store developer data and then authentication tokens through the OAuth flow. So just a quick snapshot. We have about 1,000 developers using the API. They see about 70 million requests per day, and that's all of the requests that fall through cache. We're heavily cached with Varnish and Akamai. And that all, just for our team, comes down to about 7,000 Redis ops per second. So that's about the scale that we're seeing. So I have to say, after using Redis for 2 years, we love Redis. But sometimes it's a little bit complicated. The reason why we chose it is it's fast. We can get network round trip within our internal networks in under 10 milliseconds. It's simple. The built-in data types easily translate into Node or JavaScript, although it looks like the RE-JSON module could even help us with that translation more. And finally, it's available. So the built-in mechanisms with Sentinel make it so that there's automatic failover. And for us, because it's a mission-critical system, if it's down, we're down. And if we're down, that's bad news for me specifically. All right, so this was the world as I knew it when I came into the team. So you can see here we have 4 virtual machines. We have Sentinels running on each of the virtual machines, and then we have a master and 2 slaves. And the idea here is if we send all of the reads to the 2 slaves, we could squeeze pretty much every last little query performance out of the 2 slaves by only sending the writes to masters. So this is architected to be as fast as possible and to return as quickly as possible. But as you could probably see, there's a few problems. So let's look at that. What are the problems? Well, first of all, the server and Sentinel share the same host. So if you lose one, you lose both of them. So if a blade goes out, even though we share our hosts across different underlying VM hosts, you still have the potential to lose one Sentinel and one Redis server at the same time. With 4 Sentinels, you have the ability for ties to occur when Sentinels are picking a new master in a failover. So there's actually a big red flag on the documentation that says not to do this. So pretty quickly we came in and saw, wait a minute, what's happening here? But during the failover, a slave is going to be elected master, and before that can happen, the Sentinels have to agree on who the new master should be, and that's a process called quorum. And finally, and what we're going to talk about mostly here today, is that if you're sending any read traffic to a slave, you're going to have downtime during the failover because of the time that it takes to transfer the data from the new master to the slave and then load that data from disk back into memory. All right, so let's get into the nitty-gritty of what actually happens in a failover. So these are the high-level steps right here. First, your master is unreachable. This could be time shift in the system, network latency, someone tripped over a power cable at the data center. Really, systems go down for any number of reasons. So what's going to happen? Sentinels will all start talking to each other, and they'll say, oh, have you heard from master A in so long? After a certain amount of time, which is configured by the defaults of 30 seconds, the Sentinels will elect a new slave based on who is the most in sync with master. Once the new slave has been elected to master, the master is going to do a BG save and write everything in memory to disk. And what this does is it saves the last current known state of the master. From there, it's going to sync all of its data to any of the slaves that it can find over the network. And during this time, what's important here is the slaves aren't actually able to serve traffic because they're no longer in sync with what the latest master is. Finally, once the network transfer is done, the data is going to get loaded back from disk into memory, and then the slave can serve traffic. So with 1 gig in memory, the 30 seconds is constant time. This is a default that we set for agreeing on who the new master is, or a quorum. The BG save to disk is going to take 9 seconds. The sync over the network, and we have a very fast network on InterNAP, is going to take 40 seconds. And then loading that memory back from disk into memory is going to take another 8 seconds. So overall, about 1.5 minutes. Not terrible, especially if you're in development or if you have a small data set. You might not even notice that it happened, depending. But things start to get bad as the data grows. So with 5 gigabytes in memory, it's going to take 40 seconds to do the BG save, 2 minutes to sync the data from the masters to the new slave, and then 43 seconds to load it. So 3 minutes. This is getting to the point where you might get alerted, your pager notice might go off, but by the time you SSH into the box and figure out what's happened, it's probably already fixed itself. 20 gigabytes of memory, this is where it starts to get a little bit sketchy. You're going to have about 12.5 minutes of downtime by the time it takes to execute all these steps. And then we've seen it go all the way up to 40 gigabytes in memory, which is 18 minutes in downtime. And this is where it gets unacceptable. So for us, any authenticated paths are going to fail. Any requests that fall through cache are going to fail. Your VP of operations is probably going to contact you directly and ask why you can't restart it. Well, once one of these kicks off, restarting it's not going to do anything for you. You have to wait for the sync to happen, and you have to wait for the memory to get loaded from disk into memory. So that takes, what, about 5 minutes here? Oops. 5 minutes here. So you don't want to give your VP of operations time to start looking through your code and making recommendations for how you may have been able to prevent this. So anyone who's been on call probably could relate to this. All right, so this is just a graphical view of what we were talking about before. You can see there's a linear amount of time between, a linear correlation between the amount of time spent in failover to have the sleeves become reachable, and then the size in data. All right, so the dust is settled. You're in the office next Monday, and now it's time to look at what happened and how you can actually prevent this from happening in the future. So the two main things you want to look at are, one, what's causing the failover, and two, and in our case, and maybe for other people out there as well, why is the data growing so quickly? So what's causing the failover? Well, Redis will eat as much memory as it possibly can if you don't tell it not to. So running out of memory is one way. As soon as it runs out of memory, the box will lock up and become unreachable. Two, saturated client connections. So either by using a poor Redis client, and I won't name names, but we had used one that would continually retry to connect to the Sentinels, even if it notices in a down state, or it could be a bad implementation in your application code. But if you saturate the client connections, and we got to that 28K limit on the default Unix setting, you'll also make a bad problem worse by not being able to open any new connections or have Redis communicate out to its Sentinels what the latest state is. And then finally, Gremlins. This is software, it's a fallible system. You have to have high availability, you have to be able to respond when software will inevitably break. All right, so the other one to look at is why the data is growing so quickly. So we have a lot of third-party external developers, so these are people that we don't work with closely every day. So for us, it was important to start monitoring how they were using our OAuth flow, and specifically how many tokens they're creating. So we set up amplitude for our OAuth path, actually, which is a fairly novel use of amplitude that I've seen. But we saw an interesting pattern where one client was creating an OAuth token before each authenticated call. And you can see the graph here where during peak usage, so when they have the most users, they're creating just as many tokens as they are making requests. So that was a real problem, but by monitoring it, we were able to proactively reach out to them and let them know, hey, your application isn't doing the right thing, and this is the downstream effect on us. So if you can't control it, you at least have to monitor it. The other thing to think about in terms of data, so we were storing volatile data, so the OAuth tokens, which are ephemeral and which will eventually expire and be created again, with non-volatile data, which is developer data, some playlist information, some user data. And for us, we needed to rethink about how can we separate these out so we can protect the data that can't go away, that we need to save frequently, from data where if we lost it, the worst thing that would happen is a user would have to log in again. Another thing to think about is how can we be better clients of Redis? And I alluded to this before, but there's a few steps you can take in your code to make sure that you're doing the best thing to keep Redis healthy. So one thing we instituted that's been really helpful for us was connection pooling. And we found this fantastic node module called ioredis, which has connection pooling built in it for free. Another way to do it, or another mechanism you can add to prevent Redis from going into an unhealthy state is a fast fail for connections. So one thing that the ioredis package will do is it will see if it's in a loading state from disk to memory, and it won't try to query Redis. And then finally, a back-off strategy where it incrementally takes a little bit longer each time. And the idea there is to try to let Redis get healthy before you're querying it again. So finally some code. I know you've waited this long. You can install it from GitHub or from NPM. And this is a look at our client implementation. So what we did is we forced the connection to Redis to be a singleton so that any users within our application, so any developers who wanted to make a connection to Redis, would have to go through one central place. And as you can see here, if the client already exists, you're not going to create a new connection with it. You're going to use the existing one. And I wanted to call out a few of the ioredis configs that were helpful for us. So TCP keep alive was a big one for us. If you are incurring the overhead of reestablishing a TCP connection every time you need to query Redis, it's going to be expensive for you, and it's going to be expensive for Redis. So we found we got better performance and better stability by always keeping a connection alive. Connection timeout, that's pretty basic, but you want to, if a connection has gone stale for a certain amount of time, or you're not getting a response back, the ACK back, then you can time that connection out. The ready check, I talked about that a little bit before, but there's no need to query Redis if it's not ready to actually handle the queries that you're sending it, and this can be either in a down state or if it's still loading memory from disk. And then finally, the retry strategy, it basically just exposes a function where you get to define what the backoff strategy is. So if that's every 25 seconds, and then multiply that by 2, so on and so forth. All right, and the last piece for us that was really helpful to make it more stable was to think about how we can build our data around, build our Redis environment around our data. So what was big for us was to break out the volatile versus non-volatile data, and then configure those Redis databases based on the data. So setting time to live on your keys, setting a max memory policy. And it sounds like there's even going to be a fancier max memory policy, the LRU plus LFU that Salvatore mentioned yesterday. So definitely interested in checking that out. And then also thinking about what data is accessed the most. So I think a client cache would be especially helpful for us here, where like 90% of our queries are to a very small subset of data, and then the rest, the authenticated pieces, takes up the bulk of memory, but is not queried as much. So separating those out into disparate systems where if one's unhealthy or if you need to expire keys from one, you're not affecting the main persisted store. So what that translated for us in terms of code was we exposed 2 clients. So the first client is our persisted client. This is ones that will be frequently saved to disk with the RDB save. This is where we're going to store our developer data, anything else that we can't lose. So this is going to be zipped and sent to our DR site. The other piece was the transient Redis client, and we got to set special rules on our transient client with the LRU, with the max memory, so that if OAuth tokens were to explode, or if we were to have another developer make a poor implementation against our API, we're going to be protected and it's not going to bring down the whole cluster. And then you can see we expose that there so that any developer who wants to connect to Redis has a single interface. So this is the end state now. We implemented this about a year ago. And since then, we haven't actually had any downtime associated with Redis. So what we have is a persisted master and a transient master as their own VM. The persisted slave and the transient slave are only redundant. So we're not sending any traffic to them, and in the case of a failover, they can be hot swapped. So really the only downtime now is the 30 seconds waiting for all of the sentinels to agree on who the new master should be. We have an odd number of sentinels, and they are both tracking the 2 transient and persisted masters. And then our web app talking to the single sentinel interface. That's it. So that's my information down there if you want to follow me on GitHub or email me about questions. And then a few links. So I have more details if you're interested in the details of the actual failover or more numbers. Here, you can try out NAPSTER here. We actually have a special subscription option for developers and a special trial account if you want to try the streaming service. And then Dimitri and I don't know if Dimitri's here, but we co-organize the Seattle Redis meetup. So if you want to keep the conversation going back in Seattle, you can follow the link here and find our next event, which I think is in 2 weeks.
Quick question. So you mentioned you have master slave set up. What happens if the master get corrupted data and that data being replicated to slave? How do you handle that case?
If the master has corrupted data?
Yes.
So the master's still running, but the data is corrupted within it. If Sentinel doesn't know that the master is corrupted, then it's not going to switch over to the slave. Then potentially the application would either error out, or if not all of the data was corrupted, then it would keep serving that data except for that particular key. Did I answer your question?
To detect corrupt happened and kind of isolate the master from polluting the rest of your cluster.
So if the whole thing was corrupt and it stopped serving traffic, then the failover would definitely kick in. But as far as individual corruptions within the database, we don't really have a mechanism to check for that.